SwayamPrabha. Digital India. Educated India.
Good morning, everybody. It is such a delight to welcome you to this course on conduction and convection, fundamentals and applications. I am Gautam Biswas, together with my colleague, Professor Samir Khandekar, will be teaching this course, and in the first lecture I would like to introduce you the subject, also with the resource material, and then we'll discuss about conduct of the course, and I would like to highlight some of the historical perspectives of this subject, which has emerged as a very important subject in engineering science and its various applications. Heat transfer is a subject that describes the principles of energy transfer between a heated solid and a cooler fluid, or between two flowing fluid streams at different temperatures, or from a body which is highly heated to the surroundings by a process of electromagnetic radiation. Whenever there is a temperature gradient in a body, the thermal energy flows from the higher temperature zone to the lower temperature zone. This body or element can be a solid, can be a fluid too. Heat transfer is a subject that handles the rate at which thermal energy is transferred. It is an important subject in mechanical engineering. I have already mentioned about that. It is also an important subject in chemical engineering, aerospace engineering, materials engineering, and applied mathematics. Together with heat transfer, we often use the principles of mass transfer. The process of heat transfer has many similarities with the process of mass transfer. Heat transfer occurs due to temperature difference, whereas mass transfer occurs due to concentration difference. The governing equations are similar or analogous. The solution techniques are also similar or analogous. There are many processes where heat transfer and mass transfer occur together. The subject heat transfer marches forward through new ideas, applications, and emerging technologies. The vigor of heat transfer has always come from its usefulness in various industrial applications ranging from process industries, industries connected with power generation, including thermal hydraulics of nuclear reactors, to various applications in space technologies, in data center and computer cooling, and in human bodies. The practitioners of thermal science and engineering generally deal with four basic thermal transport modes: conduction, convection, phase change, and radiation. The process by which the thermal energy diffuses through a solid or through a stationary fluid is termed as heat conduction. As we heat a metal piece, the particles vibrate. These vibrations make the adjacent particles vibrate, and so on. The vibrations are passed along the metal so that it also transports heat. This process is called conduction. Situations in which heat transfer from the body of interest is assisted by the motion of the fluid, it is called thermal convection. And when the fluid undergoes a liquid solid or liquid vapor state transformation at or very near the wetted surface, attention is focused on phase change heat transfer. We can perhaps discuss a little more about convection. The flowing fluid immediately adjacent to the body forms a thin, slowed down region around the body that is called a boundary layer. We'll study in greater detail. Heat is conducted from the body into this layer, which sweeps it away and in further downstream mixes it into the mainstream. We call such processes of carrying heat away from a body by the moving fluid convection. Now comes radiation. Radiation is a transport process which can travel even through vacuum. We have shown here the solar energy, thermal energy that we receive on our earth from the sun. And the mode of transport of this thermal energy is basically radiation. The exchange of thermal energy between the surfaces or between a surface and a surrounding fluid by long wavelength electromagnetic radiation is termed as thermal radiation. Now the subject of heat transfer is very exciting. Internationally, it has drawn importance from various well-known leading scientists. The field of heat transfer started getting enriched from the path-breaking contributions made by Baptiste Bio, or in English we often pronounce bio. And Bio worked on the analysis of heat conduction and attempted to solve the problem of incorporating external convection effects in the analysis of diffusion of thermal energy. Later we will see that in order to remember this, we use Bio number. But Bio was a mathematician. This was his fundamental contribution. Joseph Fourier, a little later, studied Bio's work and found little lacuna. His masterpiece, The Mathematical Theory of Heat Conduction, was published in French, you can see the name, in 1822. Contemporary American scientist Alan Philip Colburn conducted experiments on condensation of water vapor from saturated air streams. E.R.G. Eckert, he was basically a German scientist, switched over to United States. He was perhaps most versatile pioneer in the sciences of heat transfer and thermodynamics. During World War II, he developed methods for cooling of turbine blades meant for jet engine applications at a research laboratory in Prague. He immigrated to the United States after the war and served as a member of the National Advisory Committee for Aeronautics before taking up a faculty position at the University of Minnesota. He authored more than 500 journal articles and received several medals and awards for his fundamental contributions to the science of heat transfer. Eckert was an excellent mentor to a large number of the then junior faculty at Minnesota and PhD students. List is huge, but we get luminaries like R.J. Goldstein, J.P. Hartnett, Thomas Irwin in the list of his mentees. Contributions of long-lasting value were made by Max Jacob. Rather, he was pioneer after Fourier and Bio. Grades, Franz Grashoff, L.M.K. Bolter, Ernst Mach, Wilhelm Nusselt. In German it is pronounced as Nusselt. J.C. Peckley, Ludwig Prandtl, Lord Rayleigh, Osborne Reynolds, Ernst Schmidt, Thomas Sherwood, Shiro Nukiyama, Thomas Stanton, Samson Kutateladze, Joseph Stephen, and many other pioneers. They are no more, but the subject has reached the pinnacle of the engineering science. The path-making contributions of some of their followers has established the subject of heat transfer as one of the most prominent subjects in academia. They have been given the highest honor in the field of heat transfer, and this honor is called Max Jacob Memorial Award in honor of the pioneer Max Jacob, who contributed massively in the field of heat transfer. And this list is indeed very long. However, I would like to mention a few names. They are E.M. Sparrow, D.B. Spalding, N. Nishiwaki, C.L. Tien, Frank Wright, R.J. Goldstein, Benjamin Gibbard, Simon Ostrach, Yasuo Mori, G.F. Hewitt, Arthur Burgles, J.R. Howell, Adrian Bejan, Jogesh Jaluria, Vijay K. Dheer, Suhas V. Patankar, and P.S. Payasamy. Few others, as I said, I would be able to mention only a few I remember and can connect with their major contributions. I have mentioned their names here. In course of our discussion, you will find about their discoveries. I can tell immediately about Professor Vijay Dheer and Professor Suhas Patankar. Suhas Patankar did a massive contribution in numerical heat transfer, and Professor Dheer made almost, I would say, path-breaking contributions several times in the area of boiling and condensation. During last few years, the heat transfer fraternity has lost stalwarts like Novak Juver, he was also a two-phase flow scientist, Arthur Burgles, Moto Fuji, Yaman Ianar, Ishiro Tanasawa, Keniyasu Nishikawa, David Bryan Spalding. David Spalding, I have mentioned his name earlier. He is no more. And this year also we lost E.M. Sparrow. Though the subject of heat transfer is fundamental in nature, basically it involves analysis. Applications are found all over. To name a few, gas turbines, Stirling engines, electronic and optical device cooling, manufacturing processes, building and environmental control. The techniques include innovations in experimental science, such as the laser Doppler and hot wire anemometry, liquid crystal thermometry, particle image velocimetry, and similarly, it involves several advanced computational techniques involving finite difference, finite volume, finite element methods, spectral method, lattice-Boltzmann automata, and various mathematical approaches of turbulence and transitional flows. The principles of heat transfer in engineering systems can be applied to the human body in order to determine how the body transfers heat. Heat is produced in the body by the continuous metabolism of nutrients, which provides energy for the system of the body. The human body requires to maintain a constant internal temperature in order to maintain the body functions on a proper track. It is probably not incongruous to mention about Indian scientists who contributed staying in India in the area of heat and mass transfer. They have been able to create impacts internationally through series of contributory work, and that started with the mentorship of legendary Professor Arkat Ramchandran, then Professor S.P. Sukhatme, Professor M.V. Krishnamurti, Professor V.M.K. Shastri, Dr. B.R. Pai, Professor K.N. Sitaramu, and Professor A.K. Mohanty in the early 60s, and the tradition lives on and indeed grows. In this course, we'll follow the textbooks, very popular textbook in several institutes in India. It's a book by Professor S.P. Sukhatme. Another book also you will follow by F.P. Incropera and D.P. David, Incropera David's book, which is internationally follows maybe all over the world in many places. J.P. Holman and S. Bhattacharya, P.S. Ghosh-Dastidar, heat transfer, J.P. Holman's heat transfer. So these four I'm mentioning about the textbooks. Any of them will be helpful in this course. Also, I have given some reference study material or reference books. These are S.K. Som, Introduction to Heat Transfer, M.N. Ojicic, Heat Transfer, A Basic Approach, and a Heat and Mass Transfer book by Sengel and Gajar. So these textbooks and reference books are helpful, but if you follow any one of them together with discussions in the class and the lectures that will be delivered, it will be sufficient. The following are the topics to be covered in conduction: one-dimensional and two-dimensional steady conduction, extended surface heat transfer, that is FENS, unsteady conduction, lumped capacitance and analytical methods, Heisler charts, numerical methods. In convection, we will cover fundamentals, order of magnitude analysis of momentum and energy equations, hydrodynamic and thermal boundary layers, forced convection, external and internal flows, turbulent flows, heat transfer by natural convection, heat transfer with phase change, boiling and condensation, heat exchangers, LMTD and NTU methods, passive thermal management, theory and operation of heat pipes, limitations, modeling capillary limit, two-phase thermosiphons, and non-conventional heat pipes. Now here I have given you just a few examples of heat transfer processes. Here we have demonstrated bubble formation in film boiling. Bubbles are formed periodically in temporal sense, as you can see, and also spatially. At one instant, if we say that bubbles are formed and detached from the node, at another instant, they are being detached from the antinodes. So it's a very complex phenomena to altogether the bubble formation and dissemination in film boiling. But I have given the glimpses of the dynamical scenario. Here we have shown a typical example of electronic cooling using radial jet reattachment flow. Evolution of velocity and temperature fields can be observed owing to impingement of a radial jet on a heated surface. As I said, this heated surface is basically, the electronic components or computer chips, basically to cool the internally to cool the heat that is generated due to the electronic circuits or the chips. The flow gets reattached due to Quanda effect. Radial jet, how it gets reattached. That process is called Quanda effect. Rather, it follows Quanda effect to get reattached. So I will stop here. There are, many examples. I could have given several other examples, but I just picked up 2 examples. In course of our discussions, many such examples will come across and we'll discuss, and you will find they are indeed very exciting, sometimes challenging, to solve those complex problems. Thank you. We will meet again. Thank you for your interest.